Alright, so the last section that I have to do in Calc 2 is section 1110, Taylor and Maclaurin Series. And you know, I'm embedding what's important in 1111 and 1110. So I'm not going to have it on 1111 because it's just an estimation that's going to be included in 1110. So you can ignore what's in 1111. It's embedded in 1110. So there's not going to be 1111 section per se. Okay. So just for an introduction, so far in terms of power series, we can represent functions like 1 over 1 minus x, 1 over 1 plus x, or anything that can be written in terms of that format. In this section, we're gonna be given functions such as ex, cosine x, sine x, and the like that are differentiable, first derivative, second derivative, and so on. The question is, can we find power series representation for ex, cosine x, and sine x, and similar functions? Can we expand an infinitely differentiable functions such as these functions into a power series that converges to the correct functional values f of x? So if we're given such functions that are differentiable, first derivative, second derivative, n plus 1 derivative, can we find a power series representation for those functions? And that power series representation, does it converge to those functions? Okay, big questions. So in order to answer the questions, we're first going to talk about a few things. First, the theorem that says the form of a convergent power series so if f is represented by power series, so say f of x equals sum from n equals 0 to infinity an x minus c to the n for all x in an open interval I containing c. Then what's really nice is those coefficients an are the nth derivative at c of f over n factorial, and you can write f of x, instead of writing as a0, a1, a2, we write it as f of c. 0 is f of c, a1 is f prime of c over 1 factorial, a2 is f double prime of c over 2 factorial. Remember, this is a0, this is a1, this is a2, plus an fn at c over n factorial x minus c to the n, and so on. And we can write the power series 0 to infinity fn at c over factorial x minus c to the n. So we can write the function as a power series whose coefficients are the derivative of that function. The proof is straightforward. I'm not gonna write, there's a lot of writing there, so I'm gonna try to save some writing. So here's the proof. If you write the function and you find the first derivative, a0 cancels out, x minus a1, and that's the derivative. Do f prime at c, all these will be 0, so a1 will be f prime at c. Same thing, you do the second derivative, f double prime at c is going to be f double prime, and it's going to be 2 factorial a2, so a2 is f2, and so on. It's very straightforward proof. Now to page 90. So from there, we're going to define what we mean by Taylor and Maclaurin series. Taylor and Maclaurin series. If a function f has derivatives of all orders, like first derivative, second derivative, and so on, at x equals c. Then the series, the one we just talked about, okay? Sum from n equals 0 to infinity, fn at c over n factorial x minus c to the n, which can be written as f of c plus f prime of c x minus c f double prime of c over 2 factorial x minus c squared plus f triple prime at c over 3 factorial x minus c cubed plus nth derivative at c over n factorial x minus c to the n plus, it's a power series, it's called a Taylor series. The Taylor series for f of x at x equals c. Okay, so a power series whose coefficients are the derivatives of the function over n factorial is called a Taylor series. Now, if c equals 0, so if you're finding Taylor series of f of x at x equals 0, then that series is called Maclaurin series, and the series sigma n equals 0 to infinity fn at 0, okay, over n factorial, and then x minus 0, so it's x to the n, which if you write it out, it's f of c, f of 0 plus f prime 0 x plus f double prime of 0 over 2 factorial x squared, f triple prime at 0 over 3 factorial x cubed. This is called Mclaren series, okay? Mclaren series. So a Mclaren series is a special case of Taylor series. It's the Taylor series at x equals 0. Alright, so we have few questions here. Can we expand an infinitely differentiable function? Can we expand like ex, cosine x, sine x into a Taylor series? Okay, the answer seems to be yes. We will see why. If we can expand a differentiable function into a Taylor series, that function does converge to the series. First of all, does it converge? And if it converges, does it converge to f of x? Okay, so does the series converge, and does it converge to f of x? We have to answer all these questions one more time. Can we expand an infinitely differentiable function into a Taylor series? Does the series converge, and does it converge to the original function? Okay, so those questions have to be addressed. So here's some answers, okay? Example 1. Find the Taylor series centered at c equals 1, generated by f of x equals ln of x. Okay, so Taylor series, in case you forgot, it's so f of x has to equal sum from n equals 0 to infinity fn at c over n factorial x minus c to the n. So in our case, it's going to be fn at 1 over n factorial x minus 1 to the n. So we got to find the derivatives, the first derivative, second derivative, and so on at the end, and plug it. So f of x is ln of x. We need f of 0. Remember, it's f of 0 first. I mean f of 1. f of 1 is ln of 1 is 0. F prime of x is 1 over x. So f prime at 1 is 1. The second derivative at x is negative 1 over x squared. So second derivative at 1 is negative 1. Third derivative at x is 2 over x cubed. Third derivative at 1 is 2. Fourth derivative, we want to find a pattern, so it's negative 6 over x4. Fourth derivative at 1 is negative 6. So you can see 1 is 1 factorial, negative 1 factorial, 2 factorial, negative 3 factorial. So it looks like we have a pattern at ln of x. so you're going to see plus minus, so it's -1. So when it's even, when n is even, it's negative. When n is odd, it's positive. So n minus 1. And then 2, 1 factorial, 1, 1 factorial, 3, 2 factorial, 4, 3 factorial. So it's n minus 1 factorial over x to the n, which means the nth derivative at 1 is -1 to the n minus 1 times n minus 1 factorial if you put a 1 for x. So therefore, to write it out, ln of x equals, remember ln of x is going to be f of 0 plus f prime of 0 x minus c double prime of 0 over 2 factorial minus c squared triple prime at, sorry, 1. Why do I keep saying 0? 1. That's a 1. 1. At 1 over 3 factorial x minus 1 cubed and so on. So f of 1 is 0 plus f prime of 1 is 1, so it's x minus 1. F double prime of 1 is -1, so it's -1 over 2 factorial, which is 2. And then f triple prime at 1 is 2 factorial over 3 factorial is 2 over 6 1/3 x minus 1 cubed plus fn at x, fn at 1, which is -1 n minus 1 n minus 1 factorial over n factorial x minus 1 to the n. That cancels out an n in there. So ln of x is sum from n equals 1 to infinity, -1 n minus 1 x minus 1 to the n over n. Right there. That's your answer. Okay. So nice. Now we can write a lot of functions as power series. They don't have to look 1 over 1 minus x. Okay. Here's another one. Represent f of x equals cosine x by Maclaurin series. Maclaurin meaning c equals 0. Okay. So remember, cosine x has to be written as sigma n equals 0 to infinity fn at 0 over n factorial x to the n. So c equals 0. So it's f of 0 plus f prime 0 x plus f prime 0 over 2 factorial x squared plus fn 0 over n factorial x to the n. So f of x equals cosine x. We're going to find f of 0 is 1. F prime of x is negative sine x. F prime at 0 is negative sine 0, which is 0. F double prime of x is negative cosine x. F double prime at 0, negative cosine 0 is -1. F triple prime at x is sine x. F triple prime at 0 is 0. F fourth prime at x is cosine x. So we're going back. That's what I'm looking for, a pattern. Now repeating, f fourth at 0 is 1. You can check. F fifth at x is negative sine. So f fifth at 0 is 0. Okay, so repeating. So now we can write cosine x using that. So cosine x is f of 0, which is 1, plus f prime at 0 is 0, so we're going to ignore that. F double prime at 0 is negative 1 over 2 factorial x squared. The third one is 0, the fourth one is 1, so 1 over 4 factorial x to the 4, and then minus 1 over 6 factorial x to the 6, which equals sum from 0 to infinity. Fn at 0 is negative 1 to the n, and then it's x to the 2n, right? It's even power over 2n factorial. And all these Maclaurin series representations, they're found on table 1, page 804. So you should familiarize yourself with those ones on page 804, because I could even have you have a question like this on the test. Okay, so these have to be known. Okay, for 1 over 1 minus x, e to the x, sine x, cosine x, should the tangent inverse ln of 1 plus x and 1 plus x to the k, which we'll talk about later. So these are the basic ones that we should all know by heart.